All right, chapter 6 is slightly different from the chapters we've been doing in the past because we're talking about energy. We're going to talk about heat and how that applies to a system and the surroundings. And it tends to be a difficult concept for a lot of people because it's not matter, it's energy. And it's hard to think of it in terms of what it really is. So thermodynamics, or in this case, we're talking thermochemistry, it's talking about the energy transfer between systems. That's what heat is. Heat is energy transfer. And it goes between a system and the surroundings. And that's a matter of definition. It's how you define the system and the surroundings. The system is whatever you're particularly looking at. It could be as big as planet Earth if you're talking about climate change, or it could be as small as the reaction that happens inside a beaker. So something you can't even really see, the reaction taking place counts. The surroundings are the area around the system, and it just depends on, again, how you define the system to be. If something is exothermic, the energy transfers out. It exits from the system to the surrounding. If it's endothermic, it transfers in from the surroundings into the system, but it's always about how it deals with the system. Okay? But the problem is we can't measure things happening at the system level. What we measure is energy changes in the surroundings more often than not. Okay? And so when we're measuring energy change in the surroundings, it's going to be the opposite result for the system. And that's an important distinction to make. So an example of this is one of my favorite demonstrations is fireballs. You take methane, CH4, you react it with oxygen, it produces carbon dioxide and water in a combustion reaction. These two start at a higher energy level. And when they turn into carbon dioxide and water, they're at a lower energy level. And the difference in energy is released from this system. That is the system. And it's released to the surroundings. And so this is what we measure. We measure the temperature of the surroundings increasing. So the surroundings is taking in heat, but the system released it. Okay? And that's a really hard thing for people to understand. So we're measuring the surroundings, but the system is the opposite situation. So if the surroundings is endothermic, taking in heat, then the system is releasing it, it's exothermic. Another example, nitrogen and oxygen. It's very hard to break nitrogen's triple bond. So in order for this reaction to happen, it has to take in energy from the surroundings in order to make the reaction go from here to here. So the surroundings, where we measure it, they lose heat. The surroundings loses heat, but the process, the system, takes in the heat. Okay, and that's a really hard thing for people to recognize. So energy is the ability to do work, produce heat. In this case, we're talking primarily heat. If you take physics, it's work. Energy is one of two kinds. It's either kinetic energy, which is energy of motion. We've already talked about that a great deal. Or potential energy, energy of position and composition. So an example of composition would be methane. Because of its structure, when it reacts with oxygen, it produces carbon dioxide and water, and it's got energy built into its structure that it releases when it turns into carbon dioxide and water. And so what we need to talk about is something called state functions. In a state function, what happens is it's a process or something happening in which the value of the measurement you make is independent of the process or the path needed. It's path independent. And you're making a measurement. It's a measurement that is path independent. So, for example, talking about a state function, we're going to measure the temperature. Okay? So that means I'm going to get a thermometer out, I'm going to stick it out, and I'm going to measure the temperature in the room. Now, that measurement, does it depend on the fact if the room was cold this morning or warm this morning, and it got to the temperature it is right now. Because if you think about it, it doesn't matter. I'm measuring it right now. It's path independent. Right now, this is a state function. Okay? Because it doesn't matter what it was like this morning. It doesn't matter what it's like this afternoon. It's right now. It's a measurement made right now. How about the time for a 10-mile bike ride? So if I was to bike downhill from, say, Glenwood Springs to, I don't know, here, biking downhill, I'm going to go pretty quick, right? But if I was biking the reverse direction, biking uphill, then it's going to take a little bit longer. And so that measurement of time depends on the path I take. It's not path independent, so it is not a state function. What about the difference in altitude between Boulder and Baltimore? Okay, so Boulder's at, 5,400 feet, and Baltimore's at essentially 0. So the difference in the altitude, again, the measurement I make, doesn't matter how I measure the difference in altitude, because the difference in altitude is Boulder to Baltimore. If I get in a plane and I fly, or if I drive in my car, doesn't matter. This is a state function. However, if I decided to measure the distance it takes to drive from Boulder to Baltimore, it would be a little bit different. Because if I decided to go straight away and take I-70, which goes right into downtown Baltimore, essentially, I could measure that distance. But what if I decided to take a detour to, say, New Orleans? That would make a big difference in my measurement. So this is not a state function. Okay, temperature is a state function. That is an important thing to recognize. Internal energy, which is talks about in the book, is a state function. However, heat is not a state function. It is path dependent on how you make that measurement. For example, what if I were to measure the amount of water needed to boil, not water, heat, to boil a cup of water? So I wanted to measure how much heat that takes. Okay, so think about it. I've got a cup of water, I've got it on my stove, I'm measuring the heat, and we'll talk about how to measure heat in a minute. Certain amount of heat. But what if it was, a gallon of water? Would that make a difference? Of course it would. It's more water. It's going to require more heat to make it rise to that temperature. So heat is not a state function because it is path dependent. Okay, so temperature is proportional to the average kinetic energy of a sample. That's what we talked about in the last chapter with gas laws. Okay, that's what it is. It is a state function. Temperature is, right now, I'm measuring the temperature. Heat is not a state function. It is the amount of thermal energy transferred between two objects because they have a temperature difference. And it is not a state function, okay? So there's a difference between the two, and people get very hung up on the idea of temperature is heat. It is not heat. Heat is energy transferred. That is probably the biggest thing to recognize. It's the energy transferred between objects because of a temperature difference, and it's not a state function. It is not the same thing as temperature. And here's another important thing. The reason why heat transfers, energy transfers from high temperature to low temperature, because motion travels from fast to slow. So if I have very fast moving molecules bouncing around and they hit a very slow moving molecule, when they hit, they transfer energy, kinetic energy, energy of motion. This one speeds up, this one slows down. And when they transfer that energy, that right there is heat. It's a transfer of energy because you have fast motion going to slow motion. Okay, let me erase this stuff on here. So fast molecules have a high average kinetic energy. They're moving very quickly, and they transfer some of their kinetic energy to the slow molecules, which have a very low average kinetic energy. And what happens is the fast molecules slow down, and the slow molecules speed up. What that means is the temperature here goes down, because speed, kinetic energy, and temperature are all kind of related, and the temperature here goes up. Okay? It's never that slowness travels or transfers to fastness. Okay? It never works like that. It's always the fast molecules transfer energy to the slow ones. Okay? So there's a couple of videos on here. I'd recommend that you take a look at them. It shows how heat transfers. Okay? Heat conduction. That's what we're really talking about. We're not talking about convection or radiation. We're talking about heat being conducted between two different molecules. And it depends on the temperature differences, the density of the molecules that are being involved, because the more dense it is, the easier it is for it to transfer that kinetic energy. Specific heat we'll get to in a minute, and heat conductivity. I mean, it's a lot of different things. So there's a couple of videos here I'd recommend you take a look at. Okay, so when we measure energy, it has a bunch of different things: magnitude, units, and direction. Okay, if you've had physics, you know what a vector is. The units for energy are usually joules or kilojoules. Used to be calories, they aren't anymore. Okay, and the direction of the energy indicates where the energy originates and where it goes. And again, we're talking system versus surroundings. If the energy value is listed as negative, this is a convention that we use. A negative energy, there's no such thing as negative energy. We're not talking karma here. We're not doing yoga. Negative energy means it's exothermic. Energy is not positive or negative. It's energy. And it means it's leaving the system. So it's exothermic. If the energy value is listed as positive, it's endothermic. If it was exothermic, the surroundings increase in temperature because the heat leaves the system, okay, with high energy, moves to the surroundings, and they go up in temperature. They gain energy. Endothermic is exact reversed. If it's listed as positive, and I will try, although I don't always, but I will try to always make sure I list it as positive, it means energy is going into the system. The system's taking it in from the surroundings, and the surroundings decrease in temperature, again, because that's what we measure. We measure the surroundings, and that's what we notice, but you have to turn it around and figure out what it means in terms of the system. Okay? And here's a big thing. Energy is negative, never negative. It is a convention that is used as a shortcut. Instead of writing the words, 25 joules of energy released, we write negative 25 joules. And everybody knows that means the energy is released. So it's a convention. Okay? So let's talk about heat transfer here. Okay? So you pick up a piece of glass that's just come off the hot plate. Hot glass looks just like cold glass. Describe how the thermal energy is transferred. So this has high temperature. My hands have lower temperature. Heat always moves from high temperature to low temperature. So the heat is leaving the glass and going into my hands. If I consider the glass to be the system, it is exothermic. Okay, you twist your ankle at practice, and the trainer places a cold pack on your ankle. So your body is at high temperature, and the cold pack is at low temperature. Okay, describe how the thermal energy is transferred. It goes from the high temperature to the low temperature. So your body is losing heat, and it's giving it up to the cold pack. If you consider the system to be your ankle, it's exothermic. But if the system is the cold pack, inside the cold pack, there is a chemical reaction that takes place. And in order for that reaction to take place, it has to pull in energy from somewhere, and it pulls it in from your ankle. So if the system is the cold pack, it is endothermic. Okay, you drop a chemical in a beaker of water, notice a chemical reaction that decreases the temperature of the water. This is what I'm measuring. This is the surroundings of the chemical reactions, okay? Describe how the thermal energy is transferred. Well, the water is the surroundings, okay? It's giving up heat. Its temperature is going down. The surroundings are losing heat. That means the surroundings, the water, is exothermic. The chemical reaction is the system. The surroundings are giving up the heat to the chemical reaction. It is endothermic. Okay. Drop an ice cube at low temperature into a glass of tea at higher temperature. Heat always goes from low temperature to high temperature. So the tea is exothermic. The ice cube is taking in the heat, is endothermic. This is probably the hardest one for people to recognize, and it's something we do all the time. So you put water into an ice cube tray and you allow it to freeze. Is the process of freezing exothermic or endothermic? Okay. So when it's freezing, the reaction is, wait a minute, go back. All right, let's just add these all back in. That was really, really weird. Oh, I know why I touched the bottom. So it's H2O liquid goes to H2O solid. Okay, that's the process that happens when something is freezing. So the water, liquid, is losing energy. It's slowing down. The hydrogen bonding, the dipole-dipole, the LDFs, all of those are becoming stronger as this loses heat. Its temperature is going down. In the process of turning into this, this is exothermic. Okay, allowing something to freeze. If the process of freezing requires that this thing lose heat to the surroundings, the air, the refrigerator, the freezer, whatever it's in, it's losing heat. That means this process is exothermic. You could think about it in the reverse. If I had H2O solid going to H2O liquid, something melting, I have to put heat into this to make them move faster and turn into a liquid. This process is endothermic, so the reverse process is exothermic.